proving a function is onto can be difficult for students um, to approach. Often they're just not sure how to go about it and don't really understand the definition or how to apply it in a proof or a theorem very well. So we're going to go through one such proof just to see how each step might be motivated. So we're going to prove that basically if two functions are onto, then their composition is onto. Or otherwise stated, proving the composition of two onto functions is itself onto. As with most if-then statements, we must identify the givens and the proof portions. So here, the if part is the given, and the then part is what we need to prove or is what we're going to conclude. Okay, from this we break down, we can make our proof sandwich, so to speak. So we have our givens at the beginning, and we want to end up where we're headed at the proof, and what we got to fill out everything in between. The next question most students stuck with is, what is the next line of the proof? Yes, I write down assume F is onto and G is onto, but what do I write down next? For this, you probably want to look at the definition of onto, since you're given two onto statements. All right. The definition of onto is that if F takes A to B is onto B, if and only if, for all y and b, there exists an x and a such that f of x equals y. So remember, this means that for every y and b, I can find an x in a that goes to it. Now, I know that if I have a y in b, I can find an x. Or if I have a z in c, same thing, I can find a y in b that goes to it. The problem is I don't have any of those things to apply this theorem to, or this definition to, rather. So going forward in this case from my givens, I feel kind of stuck. So when I feel stuck going forward, what I do is I look at where I'm headed and try to work backwards. So let's look at the proof. We have to prove that the composition G composed with F from A to C is onto. Again, let's look at the definition. The definition, again, is given in terms of an arbitrary function f from A to B. Ours, however, is written as the composition G composed with F is the function we have to prove is onto, and it goes from A to C. So the first thing to do is, in order to figure out what we really need to prove, we need to translate this definition into the G composed with F. And instead of A to B, we're going to be going from A to C. So all you have to do is switch things around. So this B for us becomes C. F for us becomes G composed with F. And then you'll notice I took an arbitrary element of Z and C because that's usually what we call things in C. So, but it's the same idea. It's something arbitrary from the back end. We should find something from the front end, A, domain, such that the composition G composed with F of X goes to Z. That's what we need to prove, and it's translated now to our specific situation. So what does this mean? First part, for all Z a member of C, we need to prove some things for all. We have to take an arbitrary element of C. Before we do that, let's go and look at the rest of it. We also have there exist X and A, so we must find an element of A. That's one of the trickiest things to do in proofs, is to deal with the there exist part. And then once we find that element of A, we have to show that G composed with F applied to it is Z, our arbitrary element we chose in the beginning. Okay, so now going back, what we need to do is first focus on this part. For all Z and C, I have to prove something's true for every Z and C. The only way to do that is to take an arbitrary element of C. So that's the very first line of my proof. So again, you notice that in order to know what my next line of my proof was, I needed to go to the end. I needed to go to the prove part in order to be able to know what is the next line of my proof. Okay, I did not go from my givens. In fact, I just don't even know how I'm going to use them at this moment. All right, so I go, let X and Z be a member of C. Okay, well, so what? I got to find an X and A. How am I going to find that? Right? Now I go and look at my givens. And I say, well, let's see. This given, Z a member of C, and G being onto C, now I can use those together because remember my definition of onto is that for every element of C, there's an element of B that maps to it by G. So that gives us the next sentence. Since G is onto C, there is some Y in B such as G of Y equals Z. But now I have a Y and B to work with. B is the codomain for F, but F is onto B, so that means for every Y here, there's an X there that F sends to your element B. That gives us our next sentence. Since F is onto B, there exist X and A such that F of X equals Y. Now, because I reviewed this part down here very carefully before I began my proof, I already know that I'm going to have to find an element of A that behaves a certain way. Well, this is the only element of A I have right now, so let's try that. I need to find an element of A, and I need to show that G composed with F applied to it is Z. So I'll take that X and I'll apply G composed with F to it. Well, G composed with F of X is simply G of F of X. But F of X is Y. So by substitution, I simply get to write G of Y instead. But G of Y is Z. So now I get to replace G of Y by Z. And now I have what I wanted to show right there. G composed with F applied to the found element X is my arbitrary element I picked at the beginning, Z. This is what we sent out to show, QED.